Hi guys, Charlie here. We're going to talk about reducing finite state machines. Now, we've already learned about finite state machines and how to implement them using circuits. What we're going to deal with right now is to see if we have the most reduced version of our finite state machine and how to optimize it. The first question that we have to ask is if we have identical or equivalent states, and this is known as state equivalency. The idea behind it is pretty intuitive. What you think, well, let's say you have two different states, right? And if you give the same input to one state and the same input to the other state, right? And they give the same output, well, you can't really tell them apart, can you? So they are equivalent states, and there's a definition associated with that. It's called end equivalency. We say that two states are end equivalent when we can't tell them apart after n inputs. So let's say we put in 000 to one state and 000 to another state, and they give the same output. We will say that they are 3 equivalent if we use all different possible combinations of 3 bits, and they give the same output for each and every one of them. Now, a trick question you can say is, well, given any two states, are they 0 equivalent? It's kind of like asking, giving any two different states, right? And you can't do anything to them. It's like you're blindfolded. Can you tell them apart? Well, you can't, right? On the other side of the coin, there's a terminology. It's called indistinguishable. So if we can tell them apart, we'll say we could distinguish them. These states are unique. These states have to be in our finite state machines. Otherwise, we won't have the same equivalent machine anymore. So if we give, let's say, 3 different inputs again, let's say we give any combination of 3 bits, like 000 to one state and 000 to another state, and they give differing outputs, we say these two states are 3 distinguishable. So what does this have to do with reducing our finite state machine? Well, this plays a really large part. It's basically the crux of this algorithm we're introduced to. And what it does, this algorithm, is that it reduces our machine recursively. And the key idea behind it is that we start at 0 equivalency. We group all of our 0 equivalent states, which is a fancy way of saying that we group all our initial states because we can't put any inputs to them, so we can't tell them apart, and group them together. And then we group our 1 equivalent states. Note that for this algorithm, this is the only time we get to use the state output. After this, we'll use the next state values to calculate them. Afterwards, we will separate the states by looking at the next state values and then compare them to groups from the previous step. If the state values differ between one iteration and the next, they're not identical anymore. They're distinguishable. They're not equivalent. So we have to place them in their own unique group. And we repeat this until we hit 2 steps with the same exact groups. So we run this algorithm and we hit 2 same groupings. Now you see this is a very algorithmic approach. You could probably write a computer program for this fairly fast, and the idea behind it is that after n steps, all your distinguishable and distinguishable states are shown, and then by having identical collections for both 2 steps in a row, you say that it can't be reduced anymore. Certain terminology to note is that each additional step is called a refinement because you're making the finite state machine cleaner, or you're reducing it, you're getting rid of extra stuff, and then we can say that something can't be refined anymore after it's completed. So let's take a look at an example, a pretty simple example that demonstrates the algorithm quite well. The question asks, for the machines below, determine identical states, if any, and find a corresponding reduced machine. Note that if there are no identical states, then the reduced machine is equivalent to the original one. So we have four states here, and there has 1 bit input and 1 bit output. Um, so let's tackle this using the algorithm we just were given. And the first step is to list all our different states. Because it's zero equivalent and we can't tell them apart, we'll group them together. This is our first partition. That's what the P stands for. Afterwards, we take a look at our output. We note that for B, C, and D, their outputs are exactly the same. If you put in 0, you'll get 1. And if you put 1, you'll get 0. And that A is in its own group with giving 0 with 0 input and 1 with 1 input. So we group them by their output. So it looks like A is by itself and B, C, D are by itself. Note that this is the one distinguishable different sets. You can't really tell what B, C, D apart by giving one input. So after this, what we do is we say, okay, A is already unique. We need A. But can we tell whether or not we need B, C, and D, or are they really just the same thing? So we take a look at the next state outputs. We say, okay, let's look at state B. State B, if you put in 0, you will get D, and if you put in 1, you will get C. Now, given our P1, our first partition, our first distinguishable set, we'll say, okay, D and C are in the BCD partition, right? So, okay, we'll mark this down, and we'll keep a note of that. So then we take a look at state C. State C, if you put in 0, you'll get A, and you put in 1, you'll get C. So we take a look and we say, okay, A is its own partition, own unique state, and while C is in the BCD section. We note that AC is a differing output than DC. So we know that these two different states, B and C, are not the same. They're distinguishable. We say, okay, so we know that these two are different. Let's take a look at state D and see what happens. So we took a look at C. We will say, okay, B and C, D has B and C as its outputs for 0 and 1 respectively. So B is in the B, C, and D class, and C is in the BCD class too. We note that B and D, their outputs are within the same class that we have right here. And we say, okay, B and D, we really can't tell them apart. So we still group them together, but we know that C is different. So what we do is we put A and C in their own unique individual classes, while we put B and D together. So what we're saying right now is that A and C are unique, and we have to have them, but we really can't tell the difference between B and D. So we run this again, and fortunately it has the same outputs. So we take a look at B, and we say, okay, B goes to D and C, which we had before, and D goes to B and C, and we say, okay, D is in this set, C is in its own unique set, B is in the same set as D, and it also goes to C. So we can't tell them apart either. They both go to the same sets for 0 and 1. So therefore, they're together. We don't have to worry about A or C because they're the only one left, and we already know they're unique. So if after we do another refinement, it comes out to be the same. And that's how we know that this is the most reduced form, and that one of the sets, B and D, is not needed. So we can simplify it by reducing one state. This is a pretty simple example that helps to show you how to approach this with more inputs and more states. Yeah, that covers it. Okay, thank you. Peace.